And thanks for having me and Luke. So for those of you who don't know me, my name's Ashley King. I'm a lecturer at the Open University at the moment, and I'm joined by Luke. Do you want to say hello, Luke?
Hi, I'm Luke. I'm a lecturer at the University of Glasgow.
And so we thought we're going to do a kind of double header. So I'm going to talk for a bit, Luke's going to talk for a bit. I might come back again towards the end. But what we thought we'd kind of do between us is a bit of PR, really. We wanted to make the community aware of UKFall, which is the UK Fireball Alliance. And really, it's a collection of different groups of people who are running Meteor cameras and Fireball cameras within the UK. And our aim is to collect and recover the next UK meteorite fall. And so really, me and Luke are just the front people for this today. It's a much wider group of people who I haven't put onto the slide. Yeah, there are lots of people involved in this, doing lots of different things. And if you have any questions, feel free to put them in the box here, but to email me or Luke, or there's some links and stuff at the end of the slides. Okay, so so normally when I do talks like this, I often kick off with a picture of HL Tau, which is one of the first pictures we got of a protoplanetary disk taken by the ALMA telescope. But fortunately, we have a new image that I can use. So some of you may have seen this in the news within the last couple of weeks. This is from the European Southern Observatory. And it's the first time that we've been able to image a multi-planet system around a sun-like star. So we have, I'm assuming, I'm not an astronomer, I'm assuming this is the star up here, and then you have a couple of exoplanets out here. So these are probably giant planets, not Earth-sized type planets, but it's the first time we've been able to actually see multiple planets around a sun-like star. And so the point here really is that our telescopes are now at the point where we can actually start watching other solar systems forming. We can look at other stars, and we can see protoplanetary disks, and we can see planets accreting together. So we're actually watching the birth of solar systems and planetary systems. However, our own solar system remains the only one where we can actually get our hands on the building blocks, the materials that were there 4.6 billion years ago, and we can study those in the laboratory and actually piece together the kind of timing and different materials that went in and go into making planetary systems. So even though our telescopes are kind of getting us these amazing images, it's really our own solar system that we can use to understand how planets are made. And so we do this because we have extraterrestrial materials, and if we're really lucky and the winds are blowing in our direction, we can get money to send spacecraft out into space to collect those materials. So thinking all the way back to the Apollo missions at the end of the 60s and in the 70s, we brought back materials and rocks from the surface of the moon. There's been missions, so there was Stardust, which went to Comet Wheel 2 and brought back cometary materials. We had the original Hayabusa mission, which went and collected materials from an S-type asteroid. And we have two current active missions, Hayabusa 2 and OSIRIS-REx, which are going to start bringing back materials from carbonaceous asteroids. So Hayabusa 2 is coming back at the end of this year. Yesterday, we saw the launch of Perseverance, and that's kind of the first step towards bringing back materials from Mars. And so it's really exciting. So we can do all this kind of work to go out and collect materials from our solar system, but it's really expensive and it's very, very time consuming. So what we're lucky enough to have are just extraterrestrial materials that come to us naturally. So we get bombarded, the Earth gets bombarded by something like 50,000 kilos of extraterrestrial material every single year. Nearly all of that material is tiny dust grains, micron-sized dust grains, lots of it coming from comets, some of that from asteroids. And as this material hits the Earth's atmosphere, it's going at several tens of kilometers per second, and it basically gets burnt up in the atmosphere, and you get what we call a meteor, or a shooting star, is often what people call these when they're first sort of starting out in astronomy when they're children. I was just watching the Cosmic Cast talking about how people get into planetary science. Sometimes, though, if we're lucky, we get a much larger rock that comes into the atmosphere, so kind of meter size and above. I'll just play that video again. And when that happens, same effect. We still get this bright flash in the sky. It tends to be much larger. and we call these fireballs. And if we're really lucky, some of that rock will actually survive coming in through the atmosphere and will make it down and land on the Earth's surface. And if we go out and pick that up, that's when we have a meteorite. So meteorites are kind of natural sample return for us. We can collect those, we can study them in the laboratory, and they can tell us all about how the solar system formed. So we have meteorites. Nearly all of the meteorites we have come from asteroids. So these really are the kind of fundamental building blocks that went into making the planets. But we also have a few hundred meteorites from Mars, and we have a few hundred meteorites from the Moon. So they're really important, particularly for Mars, because they're the only samples we have at the moment. But we can compare those to things that will come back from Mars, and we can compare the lunar meteorites to Apollo samples. So it's estimated, it's not an easy number to calculate, but something like 17,000-ish meteorites fall onto the Earth's surface every single year. So it sounds a lot, but they are still relatively rare events. Nearly all of those meteorites will actually land in the Earth's oceans. So 70% of the Earth's surface is water. So most of them disappear into the sea, and we never get to actually study what those materials were. And then the ones that make it onto land tend to end up in regions that are uninhabited, so into desert type environments. And so they're never seen to come down, and they're never collected. And so again, we're kind of losing that kind of information. So I think 17,000 falls each year, but probably maybe 20 to 30 are recovered each year, meteorite falls. Saying that, we do have over 60,000 meteorites in our worldwide collections, and nearly all of those are what we call finds. So these are meteorites that weren't seen to come through the atmosphere, but have been found after arriving on the Earth's surface. And so these tend to be collected, so we know good regions to go and collect meteorites from. So these often come from hot and cold deserts, so places like Australia, places in Africa and the Middle East. Katie Joy did a really great talk the other week about the UK's efforts to go and recover meteorites from Antarctica. So Antarctica is a desert, there's a lot of ice there, but it's incredibly dry. And so I thought a good opportunity to put in this amazing picture of Roma staring at his meteorite. And so nearly all of our meteorites come from, these days in particular, come from these hot and cold desert environments, and they're what we call finds. This is fantastic, and these efforts by people like Katie and NASA to go and collect these samples is amazing, because it brings back all these materials that we have to study in our labs. There are some disadvantages to finds, though. Firstly, they have probably been sat on the Earth's surface for thousands, if not more, millions of years. And so this means even when they fall into these really dry environments, they are subject to modification by the terrestrial atmosphere. So those original components that are in them can become slightly altered. So that makes it more challenging to actually understand what those materials were like on their asteroids, and it makes it more challenging to understand what the original components in the solar system were. The other disadvantage of finds is that we basically just have a random collection of space rocks. So that's really fun, because we've got space rocks, but we have absolutely no idea whereabouts in the solar system those materials are coming from. So it's just a random, whatever we happen to find in these desert environments. And we can kind of make some guesses by trying to link them to different types of asteroid, but we don't really know, do they come from the outer solar system? Do they come from the main asteroid belt? Do they come from near-Earth asteroids? We're losing all of that context. But as a geologist, you kind of want to put your rock in place with all the other rocks where it came from. And so we're losing a big part of the information we could learn about the solar system through this. And so what we want to do when we can is to recover meteorite falls. And so these are the things where we see them coming in through the atmosphere, and we can actually go out and collect that rock really quickly. If we're lucky, we were just talking before this, we can actually get video footage of these falls, and people actually see them coming in. And so there was a big one over Southern America just a few days ago. And the advantage here is that we can recover them quickly. So this minimizes the amount of terrestrial modification these things can undergo. And that's really important for some certain types of meteorites. So this is a picture of my favorite. This is a Vuna down at the Natural History Museum. This is a CI chondrite, which is made up of lots of hydrated minerals. It's really volatile rich. It contains organic materials. It's really soft. If you touch this thing, it just crumbles. And so this is the type of meteorite that can tell us a lot about the delivery of volatiles and organics to the early Earth. But it's the sort of meteorite that doesn't survive on the Earth's surface for very long. So Avuna was fortunately found in 1938. It's a witnessed fall. But you can see at the museum, we store it in this box because it quickly gets modified by the terrestrial environment. And so CI chondrites are really rare because of this, with there are only 5. And so we want to find falls as quickly as possible so we get these really fragile materials in particular. And then the other thing we can do if we see the fireballs coming down, and in particular if we see it with multiple different observations from different locations, that we can calculate not only where that meteorite may have fell, but also work out what its pre-atmospheric orbit may have been. So we can basically work out whereabouts in the solar system that material might have come from. And so this gives us a much greater understanding on where it came from and what that can tell us about the early solar system. And so what's been happening over the last sort of, 20, 30 years is that people have been setting up dedicated camera networks to record meteors and fireballs, and then we can actually start working out where materials are coming to us from in the early solar system. And I think at that point, I'm going to hand over to Luke.
Right, yeah, awesome. So that basically sets up the scene for this key piece of information that we're missing from pretty much the entire find meteorite record. We want their orbit and ideally do a clockwork model to tie those back to parent asteroids, parent planets, or asteroid families, so we can get those rocks in context. This video, which I hope is actually rendering at some speed, is all the orbits found, observed by the Desert Fireball Network. So this is the biggest data set so far. You can see the Geminids coming in this one stream, and they're just going to hit us just about now, and we just get completely nailed by that stream just there. And so we're starting to get a clear picture of where material is getting delivered to Australia by one of these camera networks. And this is really kind of sort of fundamental if we want to understand where these rocks are coming from. All these orbits have dropped to stone. We haven't gone out to search for all of them, just purely based on funding and personnel constraints. The team in Australia is, I think, maybe 20 to 30 people. And if you take 7 per rock out into the desert for 2 weeks, and there's 1,000 orbits, that's a lot of time to be out in the desert. But the principle of networks like the Desert Fireball Network and others around the world, if we just flip to the next slide, actually,
yep.
Is you set out a bunch of digital cameras that work autonomously and just image the night sky at regular intervals, ideally in locations where you have a really nice searching environment. So Australia is really good for this, as it's a barren, lifeless wasteland. And so you put out a network of cameras, you've got substantial land mass covered. So the current extent of the Desert Fireball Network, where I was lucky enough to do my PhD, is over 1 million square kilometers, covers nearly 1/3 of Australia's land surface. And from this, they're getting quite a lot of meteorite fireball observations every year. Is this slide changed or?
Sorry.
Oh, yeah. No, sorry, I didn't know if it was rendering or not. So this is a snapshot from one camera in the Australian outback over the last 4 years from Hayden. And this is every single fireball it's seen that has dropped to stone. So as you can see, there's lots of fireballs in this image. And this is really good. And each one of those cameras is seeing all these fireball events. And so we can get quite nice triangulations on these fireballs and get an idea about their mass, about their trajectory, about their orbit to quite high precision. Just a quick bit about how we do this, actually, if you could just jump to the next slide, is the way the Desert Fireball Network does it is we take an image that's 30 seconds long and we have a alternating shutter that goes opaque, transparent, using a non-repeating sequence. So if we see a fireball that lasts for longer than like half a second, we will have sub-millisecond timing precision of when that thing entered the top of the atmosphere and when the light went out at the end of the flight. So we have a really nice idea about its bright flight, which is critical to getting the triangulation from multiple cameras to figure out where it landed and also getting that orbit. And that's been really successful. Actually, if you want to jump to the next slide. And we're able to get this trajectory really nicely. We're finding out some really interesting stuff about trajectories as a whole. One of my colleagues, Dr. Ellie Santom at Curtin University, has been basically showing that we used to assume that the bright flight line was a straight line. She's noticing it does all sorts of weird things as that rock comes through the atmosphere, including going up and down. So there's really interesting physics happening to these meteorites, even in these sort of very brief fiery transitions into the atmosphere. And through these multiple observations, we're able to get a really good idea about where this rock is going and where it's going to land. And that allows us to, actually, if you jump to the next one, find rocks. Australia is really good for this because, like I said, you can see there, it's mostly red, barren dirt. And so little black rocks, otherwise known as meteorites, stick out like a sore thumb. And this is my PhD advisor, Professor Phil Bland, finding the first meteorite from the Desert Fireball Network called Murilli, which fell in Katitanda, otherwise known as Lake Eyre. And since then, actually, if you've seen the news, I think that dropped yesterday, they found 2 meteorites in the last 2 weeks. And so they're up to 6 or 7 meteorite falls in the last few years. And each one of those has its orbit, and each one of those has its context. And so, yeah, what we're then able to do is link this rock, and in some cases, we've been able to find them within days of their fall. So without rainfall that would alter the mineralogy. So hopefully they'd have salts that otherwise are washed away by the first rain that falls on meteorites. Hopefully those will be preserved in these rocks, and we'll be able to understand a different aspect of the mineralogy, as well as figuring out where it's come from in the solar system, which is that key geological contextual information. And so that's all very well and good in Australia. We want to do the exact same thing in the UK. I'm leading, well, me and Sarah McMullen are leading a network called the UK Fireball Network, which is using the same heritage as the Desert Fireball Network cameras. So we're using digital cameras that take 30-second still images as part of a global network of these cameras. So we're aiming to cover, I think, something like 20% of the Earth's land surface with cameras, and the UK is part of that. So we've already got 6 cameras installed along the spine of the UK. Actually, we just want to, along the spine of the UK, as well as in Wales, and our first one in Scotland. And we're planning to have a few more cameras as and when WA opens its borders again and is able to deliver them to us and or build them. And so we will eventually have double station coverage over the whole UK. We have some benefits versus Australia, as we're much smaller, so we don't need 50 cameras to cover a third. We just need 12 to cover everything. We have challenges though, as we have much more city density, and so we have big problems with light pollution. So this is a light pollution map. The sort of blue and clear areas are really good for us in the dark sky parks, particularly up in Scotland. The big red and white areas like London, Manchester, Birmingham are really bad for us, or Glasgow as well, because then there's only like 3 stars in the sky, one of which is the sun, due to the severity of the light pollution. But despite all that, particularly in these dark sky areas, we can get some really nice, clear, dark areas where we can see lots of stars and even see fireballs really clearly. Actually, we jump to the next one, which will show the fireball. And so there is hope for us to be able to see fireballs and recover meteorites in the UK. So we've set up, like I said, these 6 cameras. Like I said, they're exactly the same as the Desert Fireball Network cameras, just basically a DSLR digital camera with onboard computer that has the software embedded into it that does rough triangulations and fireball detection using a machine learning algorithm, and then 8 terabytes of disk space. So these can work autonomously for nearly a year and a half before we have to go anywhere near them. and they're all attached to the internet. So if they see something, they ping their neighbors. If their neighbors have seen the same thing, they ping us to tell us, hey, we've seen a fireball. This is its rough trajectory. This is its rough end mass, if any. And this is where it came from in the solar system, which is really nice. And so we're covering pretty much the whole UK right now. This is a map of our stations. The Wales camera's not actually in there yet, but the dark region is where we could see a fireball and figure out the mass of the meteorite and figure out where it landed. And the lighter areas are, lighter pinky purple areas are where we could see the fireball and get an orbit, but wouldn't have good enough precision on the full position or the mass to figure out where it would have landed. But what's nice is we're not the only game in town, and there are a number of other fireball networks, all with the same kind of goal of recovering these meteorites. And Ashley's going to talk you through some of them that he's involved with. But it's basically a nice thing that we're all looking at the sky to get the same goal.
Cheers, Luke. Sorry, I was a little eager with my slide moving. Yeah, so as Luke said, the UK Fireball Network is not the only camera network operating in the UK, and this is why we thought we'd take the opportunity to kind of do this talk, is to explain the different networks that we have. So I'm largely involved in SCAMP, which is the System for Capture of Asteroid and Meteorite Paths. You can imagine we had a lot of fun trying to come up with a name for this. So there's just a little picture here of a kind of SCAMP system that hasn't been installed, but they effectively consist of an all-sky video camera that you can see here. This plugs into the back of a computer, and then that computer sends everything to a server. So it's a really simple system. These cost about £1,500 to £1,700 or so to put together. And so we have, this is where the cameras are currently situated for SCAMP in the UK. So there are currently 6 cameras operating. So there's one in Canterbury, Honiton, East Barnet in London, one at the museum in Cardiff, the Armagh Observatory. There's one at the University of Manchester. We had planned to install one in Rochdale, which should be happening right this second, although I'm not quite sure exactly with the lockdown in Manchester whether that's happening, but there's a camera ready to go for Rochdale. And then we have plans to kind of put in extra cameras up in the North York Moors Park and down at Easter at Harwell. Ideally, these cameras should be about 100 kilometres or so apart. So you can see from this map that we have a long way to go in terms of our coverage of the UK with SCAMP. However, as Luke said, we have other cameras in other networks, and so this is kind of where the idea from UKFall came from, was trying to combine the efforts to do this. And so SCAMP is actually an extension, or is part of the FRIPON network, which operates in France and has been for a few years. So I believe, somebody might correct me, but I believe FRIPON means rascal in French, which is why we came up with the name of SCAMP. And so they currently have over 200 cameras, largely in France, and covering all of France as well. They've got a lot of money to do this. But also there are a few other kind of add-on systems. So there's Italy is really well covered by FRIPON. So I think that's called Prisma. There are some cameras in Germany. Going out to Hungary and Romania also have some cameras. So FRIPON is really kind of extending over Europe. And I think the Italians, the Prisma system, were the first to actually recover meteorite fall, either earlier this year or towards the end of last year. There have definitely been a few falls in France, but the search terrain is quite difficult. So I think so far they haven't actually recovered anything, unlike the Desert Fireball Network over in Australia. And so this is just a little cartoon of how the FRIPON or any camera system works, really. So these, as I said, they're all sky video cameras. They record about 30 frames per second, I think it is. And so when the system detects movement, it will actually save that footage either side of that movement. It then uses the movement of the object. It basically tracks it against the background of stars to work out which direction it was traveling. It then saves that data, feeds it into a server, And if you have multiple detections from different cameras, you can start calculating the trajectory of that object, how quickly it was going. You can start piecing together the pre-atmospheric orbit. And then with a kind of a bit of magic involved, you can work out the dark flight. So you kind of feed all that information into a sort of atmospheric model. So which direction were the winds blowing? What was the weather like? And you can actually work out what's going on. So dark flight is after you've had that bright event and you're trying to work out where that rock has fallen as it drops out of the sky. And these things can be blown quite significantly away from the kind of direction that you thought they were traveling. And as Luke just said, apparently some of these things may not be moving in straight lines in the sky either, so that's not going to make life any easier. But with multiple observations, we can start piecing together some of that, and we can make our estimation of stream fields much more accurate. So this is just a very short little video from one of the SCAMP cameras. This is earlier in April this year. This is the one in camera in Cardiff. So you'll see a little bright fireball just comes in down here. So this is the moon over here. So this was actually seen by 4 or 5 SCAMP cameras, plus a whole load of other cameras. And so we were able to kind of piece together whereabouts this came from and work out quickly that it probably wasn't a meteorite dropping event. Ooh. And then there are other camera systems operating in the UK. So the UK Fireball network and SCAMP cameras are really kind of set up to detect fireballs and deal with fireball footage. So to help us try and look for those brighter events that are potentially meteorite dropping. However, there are other networks, including UKMON, which is the UK Meteor Observation Network that's been going for quite a while in the UK. And there's also Nematode and the Global Meteor Network have also started putting cameras into the UK. The Global Meteor Network is really interesting because it uses a Raspberry Pi system. So you can have some fun playing around with coding and things with that. And these networks tend to use or do what we call narrow field meteor surveys. So they, UKMON, for example, uses a CCTV camera, which is basically points in one direction. So if you want full coverage of the sky, you need to put cameras all the way around your house or your building. And they are really, really good. So the CCTV camera is designed to work at night. So they're really good at picking up faint meteors. They sometimes struggle with the brightest fireballs because the cameras become saturated. And so what we're trying to do is these networks, we have several different networks working in the UK, but really they all kind of complement each other. Each of the camera systems does slightly different things. And so we can piece all that information together to work out orbits and stream fields for any meteorite events. And effectively, the more cameras we have, the better coverage we have over the UK skies. That increases our chances of detecting events. It's a big problem in the UK because our weather is not particularly good. So you'll have a camera that won't see an event because it was cloudy, but other cameras that would have picked it up. And so really by having more cameras, what we want to do is increase the chances of detecting these events. And that significantly improves the accuracy of our pre-atmospheric orbits and trajectories and velocities and stream fields. And just in this figure in the corner here, I know it's a little bit small. This is just to give you an idea. This is all the Meteor Fireball cameras that are currently operating in the UK today. So you'll see the symbols of different networks, but what hopefully you can see is that we have pretty good coverage, particularly around London, as you can imagine, but decent coverage in the south. A little bit, it gets a bit patchy in the Midlands, but really lacking cameras kind of out in East Anglia. Wales isn't particularly well covered. The north of England and Scotland as well. We still lack coverage. So even though we have all these networks kind of operating, there are still places where we really need to start installing more cameras. And so we were quite aware that there are all these different networks are quite confusing. They all have slightly different acronyms. They will do slightly different things. And so we thought we'd chuck yet another acronym at you. So we came up with the UK Fireball Alliance, so UKFall. And effectively, so I'm not going to name all the people who are involved in this, but you can see there are lots of different organisations and groups involved in UKFall. And really our idea was to coordinate the efforts of the camera networks. So can we pull all the data together between the different systems so that if there is a meteorite dropping event, we could recover it quickly. So our aim really is to recover the next UK meteorite fall. And to do that, we want to maximise all these networks. So rather than having 5 or 6 networks, each with their own different data sets, We want to make it so these networks all talk to each other. We can work out where that meteorite may have fallen really quickly, and then we want to coordinate efforts to go and collect that sample, analyze that sample, and curate that sample. And so, fortunately, everybody's kind of been on board with this, and we're starting to pull all this information together under UKFall. And this is just to give you an idea that this isn't a complete pipe dream to recover a UK meteorite. We are quite small in terms of our land mass, but there are UK meteorites. So there are 18 official meteorite falls in the UK and 6 in Ireland. Over the last 200 years or so, on average, there's been 1 fall recovered every 9 years. So it does happen. And we can estimate, actually, that on average, there's probably several small meteorites that land in the UK each year. Trouble is, you have to detect it, and then you have to find it. And so if you've got a really tiny meteorite that's a gram or 2 of material, and it lands in a remote part of Scotland, we've got absolutely no chance whatsoever of actually recovering that material. However, the more cameras we have operating in the UK, the greater the chances are that we might actually be able to get our hands on some of these small meteorites that are landing in the UK. I think Luke's going to talk about some of the previous meteorites in the UK.
Yeah, so like I said, we've got pretty good, or reasonably good heritage in the UK of finding meteorites after they've been observed to fall. The most recent one fell in Glasgow on the 5th of May, 1991. It was an ordinary chondrite, type L6, so sort of a pretty common run-of-the-mill type of meteorite you would have in our collections. And it was found by this chap called Arthur Pettifor, whose priority seemed to be less, oh man, awesome, I've got a new extraterrestrial meteorite that just landed. He was just more preoccupied that it nearly damaged his greenhouse, which I guess gives you a window into the priorities of an elderly man in 1990s England. Now, the last one in Scotland was Strathmore, also an L6. Not sure what it is about L6 chondrites and falls in the UK, but they seem to have an overabundance. This fell in Strathmore in Scotland in 1917, so over 100 years ago now was the last one. So we're overdue one in Scotland. This was an airburst event, so that fireball broke up into 4 small pieces in the top of the atmosphere. And lots of pieces sort of like landed around the area, and they were able to collect all these fragments of this meteorite. It was quite a large event. One of them, in fact, nailed a lady's house, as you can kind of see here. Though Monica Grady would tell me to take great pains to tell you this is one of the first examples of fake news, because although it did hit the top of this lady's house and create a sizable hole, by the time the meteor had got there, they'd fixed the hole, because you don't want a hole in your roof. So in a sort of kind of fabrication, the journalist used a black marker pen and drew on the hole on the picture. But yeah, and again, similar to the England event, the news reports around this time were hilarious, talking about communities thrown into a state of consternation, and they heard it fizzing, which kind of gives you a window into sort of the mindset of 1910 Scotland. I believe the next one is Barwell, which I'm
going to talk about. So Barwell is the Christmas meteorite, because it fell on Christmas Eve, technically, 24th of December 1965. It's the UK's largest meteorite fall, so I think it's about 45 kilos of material. So a big event. Again, it's an ordinary, I nearly said boring then, they're not boring, they're all meteorites. It's an ordinary chondrite, as everything is in the UK, and as most of our meteorite collections are. And so this is a really nice one for finding, because it hit things. So I always say, people ask about how we're going to find the next UK meteorite. I always say that the ideal situation would be it hits someone's car, or hits a building, or hits somebody, because that makes finding that meteorite so much easier. There was actually a new meteorite fell in Tokyo last month, which I believe was found because it hit the side of a building in Tokyo. Anyway, so this is, some pictures that Natasha at the Natural History Museum dug out of the archives of Barwell, and the recovery of Barwell. So we have an excellent scientist with cigarette hanging out of his mouth. So proper curation procedures here as he's measuring this crater. So Barwell was big enough, it made some little impact craters in the roads in Barwell, which is just outside Leicester. Some of these stones actually bounced up and went through people's windows. So there were stories about bits of Barwell being recovered out of a vase that had just been sat on somebody's windowsill. Some of the local residents called the police because they thought there were youths and hoodlums throwing rocks at their cars and at their buildings and things. There's a nice picture of one of the policemen in Barwell here with a piece of the stone. It generated lots of news in the national and local press. So this is just a cutting that Natasha found. I think it's from the Daily Mail, Catch a Falling Star, and their little subheading here, put money in your pocket. Unfortunately, I think people are going to be disappointed if they think they're going to make significant amounts of money out of recovering another ordinary chondrite. Yeah, back to you, Luke.
Yeah, and so that kind of brings us back to the present day where we haven't found a meteorite for nearly 30 years, and considering some 1 or 2 should fall every year, we're batting way below our average. And so hopefully the UKFall will sort of aid that. And we've had a number of successes in some ways. And first, just can we see the same event as everybody else? So this was an event that fell actually in Belgium on the 15th of February 2019. And the Frippon network and loads of amateur astronomers caught it in Belgium, which was great. UKMON caught it from England, and we caught it as well in the UK Fireball network, which I think is the next image. Before you get too excited, that big bright thing in the middle is not the fireball, that's the moon. The fireball is actually off to the right, that little thing just going behind that tree there. Yeah, highlighted by Ashley very nicely there. And so it's kind of cool that we can see stuff falling in other countries as well. So we've got quite a large field of view. And we were able to get a nice orbit for this and unfortunately model that it didn't drop a stone, despite how big it was. We also, this one was kind of nice because I just installed this camera on the 27th of October. And that night it saw this fireball. Unfortunately, it was the rest of the cameras in the UKFall network were clouded out, but an amateur astronomer by the name of Jamie Shepherd saw the exact same event. And so we were able to, again, sort of combine that data set, which was really nice. And we had then 2 observations. This got us kind of thinking that we really need to get a way for all our data to talk to each other quickly, particularly after this event happened. This was like the money shot, which kind of showed that all of this could work. So UKMON saw a fireball on the 16th of February 2020. We saw the same one with one of our cameras. Scamp, I think, saw it twice from 2 different events. And so pretty much every UK network saw this event. It was very big, very bright. And we took some time to reduce the data in lots of different ways and combine it all. And we could get an orbit for this rock. And what was really exciting is the models would suggest that there is about 10 grams of material at the end of that fall line, which is not tiny, not massive, but also not small. It would be like on the order of like a golf ball, which is eminently findable. There's just one problem, is that it landed in the North Sea. So that was unfortunate because obviously scuba diving even for that would be challenging. But what that shows is that we can combine these data sets and get a good idea about where this thing's falling. And so Jim Rowe, who's part of the Scamp network, has been doing a bucket of work writing a code to allow us to talk to each other rapidly. So if we all see the same event, similar to the one that fell in the North Sea, but this time hopefully on land, we can share that data in a uniform format and get an orbit really quickly. And we managed to do that on the 3rd of January, where a bunch of our camera networks saw the same event, the same fireball. We were able to transfer the data between all the networks and run it through all our different codes and they all came out with roughly the same numbers. So these two orbits down the bottom are calculated through two different data pipelines, one through the Frippon system and one through the Desert Fireball network system. And those orbits are roughly the same, which is nice. And again, unfortunately, this one burnt up in the atmosphere, but hopefully we're now ready to rock and roll when the next meteorite dropping fireball comes through our atmosphere, and hopefully go find it. So we'd like that to happen after the COVID pandemic is over and we're actually allowed to go searching. So that's kind of the run of the play in terms of finding a fireball. But another thing we've kind of realized is we have essentially getting towards a global observatory now. And in the UK and elsewhere, we're having so many eyes on the sky at all times. We're basically acting as a very wide field optical telescope. We obviously don't have the resolution of the bigger, like the very large array, etc. But because we're on the sky all the time, we tend to be the first people to pick anything up. So believe it or not, we were actually involved in the recent LIGO manuscripts talking about the Neutron star merger, because we were the first people on the sky, we could constrain its maximum or minimum maximum brightness, because we were looking at that part of the sky at the same time, and we know the resolution of our kit. We've also got the sensitivity to pick up satellites, so we can start to produce a real-time data set of satellite orbits and figure out where things are, which is really useful for stuff like planetary defense. And there's a little sort of thumbnail in the top left there, which was a near miss between the Gemini and Fermi satellites, one of which was out of control and the other one had to make evasive maneuvers to get out of its way. And those kind of things are going to become more and more common as the local space environment gets more and more crowded. And so being able to have this real-time data set of where stuff is going to be really important going forward. I also know UKMon's been doing some awesome work looking at sprites, which are these vertical lightning strikes that happen at the top of sort of thunderhead clouds. And they're very rare events, are very rarely caught on camera. But again, so if there's a nearby storm that's producing these, UKMon and/or UKFN and/or Nematode and/or Scamp will see it. And so there's some really nice sort of weather patterns we can look at. There's, again, like satellite orbits, even aiding in mission flybys. So we saw the OSIRIS-REx do its Earth pass on its way to the asteroid Bennu. And so we're able to, as well as doing the fun meteorite recovery, we're able to kick into some really hardcore cosmological and astronomical problems, just because we're seeing that much of the sky all the time and saving all our data, which is petabytes now. Not sure how long we'll be able to keep that up, but it's kind of this extra fun bonus. Just by being there, we're able to tuck into all these other problems that we didn't design the kit for, but still seems to work. And as well as all this, we've developed an app where anyone can kind of help out. And this, again, works. So it's an app called Fireballs in the Sky. You can download it on Android or iOS. If you have a Windows phone, sorry, it doesn't work on that. I also bought one of those, and we learned from our mistakes. And so this app allows you to, if you see a fireball, basically report it using the inbuilt GPS and gyrometer. You point at the area of sky that the fireball started, click, see where it ended, click, and then you can say how long it took. Did you hear a sound? What was its color? How did it fragment? And so you can get a really good detailed observation of that event that has reasonably good precision as well. We actually found the Dingle Dell meteorite because someone used our app to report that in Australia, and that added the extra viewpoint that we needed to the north of the fireball to be able to triangulate it. And so this is like really useful little tool, and I would encourage you all to download it and sort of help with our efforts. Kind of like, I hope we've hammered home by now, the more eyes on the sky and the more observations we get, the better our triangulation and models will be about where this thing will land. And I'll pass back to Ashley just to wrap up.
Yeah, cheers, Luke. Yeah, so that's kind of what we've been doing and what UKFall is. So hopefully Luke has kind of nicely demonstrated that we're in a kind of good place in regards of the kind of data pipeline. So we're now at a point where we can kind of pull all the data from these different camera systems and use that to calculate these trajectories, pre-atmospheric orbits, and these strewn fields. And so really the next step is actually going out and collecting a meteorite. Now we have to wait, obviously, for that event to happen, and we can't predict when that might happen, but hopefully we're in a good position now that we could actually get people on the ground really quickly, and that's kind of where UKFall is at the moment. We are working on kind of coming up with guidelines for how we go about collecting meteorites. Obviously, if there is a meteorite fall in the UK, it's likely that it would have been a large fireball. We are a densely populated island, so it's really likely that people will have seen that, even in the middle of the night, people are up and about and doing things. And so often kind of our first indication that something's happened is, somebody posts something on Twitter, they saw something. And so, yeah, we're hoping, we can kind of react quickly to that. We can put advice and guidance out on social media and in the local and national news. As often, every now and again, you get a bright fireball that makes it into the papers and things. Anything with a meteorite almost certainly will be bright enough to generate some interest. Once we've calculated where that meteorite has fallen, then we have to think about complications over how we collect that sample. So, as I said, if it falls in central London, that would be kind of handy. But if it falls in the Lake District, we have to think about how we would search there. If it goes into a forest, how do we search there? If it falls into some mountains, how do we search there? So there are lots of kind of local issues that we'd have to consider for hunting for meteorites. And then we have to think about land permissions and stuff like that. UKFall is now affiliated with the Geologists Association, which is quite nice. I think our plan at the moment, we do have kind of a nice sort of pipeline for how we would go about this if it happens. So our plan at the moment is probably for a preliminary team to go and search. But what we'd really like to do is get the general public involved in this. So planetary science, meteorite falls, fireballs are a really great way of engaging people with UK planetary science research. And so our hope is, there are lots of complications involved in trying to do that, but our hope is that we could get the local public and local societies and groups to help us search for these things. The more people we have on the ground, the greater our chances of finding that 10-gram golf ball that may have fallen from space. And you can see in the background, this is a picture from a search in France, just as they went into lockdown earlier this year. You can see everyone wearing a face mask out hunting for these tiny little rocks. I don't think they recovered anything on this one. We're also putting together guidelines for people, so if they do come and help us search, they know not to put a magnet on anything and important stuff like that, and how to not get themselves into trouble. And also working on a kind of collection kit, so proper bags, proper gloves, GPS system, if we can get a portable XRF, all that kind of stuff that's kind of been held up a little bit because of the lockdown. And then the really important thing really for us, from a kind of science point of view, is how we analyze that sample and whereabouts and how we curate that. And our aim really is to kind of use all the expertise across. We're not keeping this a closed club. We really want people to be involved. We really want people, if you want to analyze a particular piece of a meteorite or have particular expertise, we're very open to sharing this. This isn't, I don't just want this meteorite for me to sit in my lab. So really I'd want to encourage you, if you're interested in being involved, either in just being on the UKFall mailing list, or if you're really interested in having a camera, please let me or Luke know, or get in touch with any of these organisations. They're all lovely people. So I've left all the links here. So I think this is being recorded, so you can track these down. But yeah, feel free to give us a shout. And otherwise, I think we are done, Luke. So we'll take some questions.
Yeah. Thanks for having us.
Yeah, thank you very much.